Hello everyone, I'm Yukun Zhou. I come from Shenzhen Institute Advanced Technology Chinese Academy of Science. Today, I'm very honored to introduce a paper titled an efficiently encrypted deduplication scheme with security enhanced proof of ownership in edge computing. In the big data era, IDC predicted that the digital universal will reach 175 dB in 2025. Edge computing has become a very important thing. According to IDC, there will be 36% of data at the edge transferred to the core each year, and will be increased in the next 2 years. The flow of massive data from the end to the edge and the data center will bring greater challenges to data storage and management. According to the analysis of many institutions such as IBM, Microsoft, and there are many redundant data, and it is widely stored in the storage system. Specifically, more than 90% redundant data exists in the backup system. How to store and manage this data? We usually use data deduplication. Data deduplication is a lossless compression technology to eliminate the redundant data. Deduplication can reduce storage space, save network bandwidth, and enhance SSD lifetime. It can be classified into field level or block level, client-side and server-side deduplication. Deduplication generates a field or chunk or block tag to represent the whole file, and only one copy of the same data is stored, and others refers to it. This is a simple system model of the edge computing deployed with data deduplication. Edge computing can be seen as a three-tiered architecture. The central cloud. The central cloud stores and retrieval data from edge nodes and the user. The edge node provide limited computing, indexing, storage, and other service. For example, some papers for AF dedupe and some enterprise products also use this architecture. However, it faces some security challenges. For example, data confidentiality and privacy leakage. For example, brute force attack and duplicate phishing attack or replay attack. We will describe it above. The fourth challenge to protect data confidentiality. Different users always use their own key to encrypt the data. Thus, the same data will be generated into different subtexts. Users propose to solve this problem. Users propose convergent encryption or message locked encryption to solve the problem. The keys are derived from the hash value. Thus, the same data will generated into the same key, and we can perform deduplication over ciphertext. A similar algorithm is random convergent encryption. It uses a random key to encrypt data, and encrypt the random key use a MLE or CE key. However, message locked encryption or convergent encryption suffers from brute force attack because the keys are deterministic and keyless. What is brute force attack? Brute force attack is attack over the ciphertext. For example, a message, we know a message is in a known site as the attacker knows the ciphertext, the target ciphertext C, and it can encrypt all the data in the known site and compare the ciphertext with C to recover the message. To resist brute force attack, some researchers propose server-aided encryption. However, it is time-consuming and not suitable for fine-grained deduplication. The second challenge is the privacy problem. We all know client-side deduplication not only saves the storage space but also saves the network bandwidth, because we only need to upload the fingerprint of the field tag to the central cloud. If the fingerprint exists, users do not need to upload the field content. However, it suffers from duplicate phishing attack and privacy leakage. What is duplicate phishing attack? Attackers try to get the fingerprint from with some method, and he tried to download the private data belongs to other users and perform CDN attacks. Researchers propose proof of ownership to solve this problem. It is a challenge and response protocol, and which can verify the ownership, the ownership, and achieve authorized access. Then we will destroy the state-of-the-art proof of ownership. There are mainly two methods: Merkle hash tree based POW and Bloom filter based POW. As we can see, the MHD POW is client and server need to also to construct a Merkle hash tree, and the server randomly select and leave node index as the challenge information. The client returns the path information from the lead node to the root node. Finally, the server verifies the root nodes. However, it is time consuming because the encoding process and the construction of Merkle hash tree is time consuming. To reduce the computation overhead, we also use the Bloom filter based POW. It divides fields into blocks and generate tokens to create a Bloom filter. However, it will suffer privacy leakage due to the false positive of the Bloom filter. We get some observations, and more than 90% of the redundant remains in the cross-domain duplicate field and duplicate blocks with users. And the observation 2 is edge node connect with central cloud with WAN, which faces more security risks. Users connect to the edge with LAN, which is protected by a lot of security methods. This motivates us to propose SEPOW, which can adopt different encryption and deduplication algorithm and intra-edge and inter-edge. Thus, we can achieve balance between security and performance. This is the system model of SEPOW. We consider central cloud, edge node, and user. Central cloud provides the central cloud storage service. The edge node provide computation and storage with limited resource, and users provide encryption and download request. This we present a local aware hybrid encrypted deduplication algorithm. We propose inter-edge file level deduplication and intra-edge block level with different tag generation and key generation. The field tag is generated by twice hash function, and the file key is aided by a trusted H node where RSA oblivious protocol. And we also use user generated mass locked keys and try to encrypt the blocks and transfer the subtype of block to the H nodes. Users protect the MLE keys with the file key, and the H nodes re-encrypt the subtype of blocks with the master key and upload to the central cloud at last. We also give a security enhanced POW algorithm. It is a dual level. We also in the initialization path, we divide field into blocks and compute the tag tokens and construct a cuckoo filter and insert the tokens to the cuckoo filter. Also, we compute the algebraic signature, and we to resist the replay attack at the field ID and block index at the unique label. We also give the challenge and response in the POW. This is the first download process of SEW. And this is the subsequent upload of SEPOW. We also discuss the above. We give some security analysis of SEPOW. We can resist brute force attack because we can generate random and secure keys at the field level and block level. We give this is our evaluation. We use the statistic data and real world data set to we use the cumulative time and upload time as a metric. In figure compared with server-aided mass lock encryption, SEPOW reduce encryption overhead, which is close to RC and to NCE. In the figure C, the cumulative time increased with the field size compared with the MHCPOW. SEPOW reduced about more than 70% cumulative time overhead because the individual coding and construction of more high tree is the MTPOW incurs large time overhead. In the figure A, compared with the BFPOW, SPPOW only increased 7.7% metadata cost because we need to store extra algebraic signatures. We compared with the MTPOW reduce more than 20% subsequent upload time. This is our conclusion. We propose SEPOW with a location-aware hybrid encryption scheme with different encryption algorithm. We also propose a dual level and security enhanced proof of ownership. The security analysis demonstrated that the SEPOW can ensure data confidentiality and resist the privacy leakage. That's all. Thank you.